this is a Nikon Z30. Now, what is the difference between this camera and all of the other cameras around this size and price range, you might ask? Well, that's a good question. And I don't actually know exactly. But let's just talk about how cameras work so that we can get to the bottom of this, at least to some extent. Now, cameras capture waves of light, just like waves of sound. But instead of pressure waves, which simply move atoms forwards and backwards, and there are no subatomic particles emitted as a result of sound pressure waves, there are subatomic particles emitted as a result of various interactions, atomic interactions, such as heat, for example, things like this. And one of those, a lot of those interactions lead to the emission of photons, which, just like sound waves, are represented as waves in physics. That is a one-dimensional drawing of the simplest wave possible, called a sine wave. So this one-dimensional drawing is our entire knowledge of all of physics combined. This is like the key to the universe that we use to do everything in science. And so once you know about this, and you can visualize complex waves which look like this, which is just a interaction of lots of different types of sine waves, then you start to understand everything in physics. And I'm going to put a link in the description now. I forgot how to write. Hold on. It's called Branch Education. There it is. That is a YouTube channel, and you can find it's possible to learn all of physics and electronics from this YouTube channel without ever doing any maths or going to university. So people get very confused with the numbers, and these are really good 3D animations of microscopic electronic devices, and they tell you how they work in simple language, and they describe them. And once you can visualize those things, then you can put any kind of numbers you want into them. That's not a problem. But to kind of understand what they're talking about, where they're talking about an electron, because an electron is in physics a particle which is represented as a point in space, which usually is represented like a dot, and it's also a wave. So that is not a logical thing to think about, because that's not how the human brain functions, and that's what everyone has trouble with. That sounds funny, but look it up, that's what it is. So if you think about electrons, which is what electricity is, it's a flow of electrons, it's actually a wave. In fact, it's a sine wave, because sine waves are the easiest to manipulate. When you say it's a sine wave, you imagine a wire, and you kind of imagine something like a pressure wave, which can be a sound wave or any kind of pressure, pushing at one end of the wire. And for every action, there's an equal and opposite reaction. And so this push then has a pull effect, which then has a push effect, which then has a pull effect. It's like a thing that happens like this. So that would be the push effect, and that would be the pull effect as a result of it. So as soon as you push something, it'll kind of have a resistance to you, and it'll kind of resist you to some extent. depending on what kind of material that is, let's say it's a wire. Wire has very high conductivity and very low resistance, which means if you push it, it will have a very good reaction to it. And that means that the phenomenon that occurs in conductors, which is these wires, is that they conduct electricity. That's why they're called conductors. But if you had a piece of wood and you pushed voltage through it, voltage is represented as a sine wave, but it's not a flow of electrons, whereas a current is also, everything is represented as sine waves. They just mean different things, but everything is just like this complex interaction of these waves. And in field theory in physics, they call those fields as well. So in conductors, when you push electrons or voltage through it, it will have this initial reaction of a push, and then it will have an equal, basically, reaction back at you. And then this reaction, then how do I explain this? It's like a pendulum. When you swing a pendulum, it just keeps going like this. And so something that has no resistance will just keep going forever. And something that has a lot of resistance will kind of just stop. So that initial push is represented as this curvature up. And then if it has a lot of resistance, you can represent the reaction to it. Realistically, the next wave would be smaller in size, for example. Okay, well anyway, that's the entirety of my 4 years of full-time study in acoustics, physics, and electronics. That's basically, if you know that, you know everything. So everything else is very easy. So these are just complex representations. The easiest way to think about it is, so this is light. This is like what light is made of, and that's what these cameras are capturing. So the easiest way to think of it is ripples in a pond. So in the first class of acoustics, I think it was the first 3 months that I did this out of 4 years. They introduced this concept of waves, and they show you a puddle, a picture of a puddle, and when you drop a little pebble in the puddle, it creates these ripples like this. And that's the best way to visualize it. And you can see it in the ocean. This is the push effect, and that's where the surfer is on the surfboard. And then that wave then comes down. Every reaction has an equal and opposite reaction. It comes down and crashes. That is what waves are. That is what happens here. And through all this scientific observation and experimentation, we found out that something called voltage behaves like this as well, and we can manipulate it through wires and circuits and electronics. Voltage is a phenomenon. It's basically described as, it's not electricity. Voltage is not electricity. Voltage is potential of a current to move from a high potential to a low potential. This is the high potential, this is the low potential. And under certain conditions, voltage is created. So when there is more electrons in one area, electrons are represented with this negative symbol. They simply want to move to an area where there's less of them. That's all it is. So you have a battery here. The battery represents more electrons on this side and less on this side. You connect the two ends together and they just start flowing from one end to the other. That is also how magnetism works. So this is like looking at the pond upwards. Now what happens, like you're looking down at the pond and you throw a pebble and you see these waves. But then as a result, in most of physics you have refraction, reflection, and a bunch of other things, diffusion and stuff like this. And in lighting, they talk a lot about diffusion. But if you keep this in mind with this pond thing, when this wave reaches the wall, it'll bounce back, and that's when this becomes a complex wave. You can see it visually when it hits this wall. The ripples become like more complicated, and then you start having these complex waveforms. Human speech is a complex waveform. It's made up of a fundamental, which is the strongest part of it, and the harmonics. And so learning how audio circuits works is actually more complicated than learning how electrical circuits work, because it's about complex waveforms, whereas electrical circuits are mostly about these simple waveforms. So you're combining and manipulating complex waveforms when you're doing audio or video, because color is also complex waveforms. And that's it. So that's basically what you have to know to finish a master's degree in some kind of physics acoustics area. And so cameras capture complex waveforms, but they're not as good as the human eye. So this is a lens of a bigger camera, and this is a lens of a smaller camera. And so depending on, so cameras need a lot of light because they don't work like the human eyes. The human eyes are a lot more complex and they work kind of differently. That's an eyeball in a socket, I guess. There's a nerve going to the brain as well. There we go. Brain. Okay. So to maximize so this is the biggest problem with small cameras, is to maximize the amount of light. To maximize the amount of light, complex waveform. It comes in here, they actually curve the lens, so it's got this dome shape, because they can get more light in that way through the side, like this. Whereas with the bigger cameras, because the lens itself is actually bigger, they don't really need to do that. And the other thing they can do with the lenses that are bigger is they put different kinds of glass in there of different shapes. And that different glass of different shapes has different effects on the on how like distance things at a distance work compared to things that are close by. So how do you explain that? So obviously you can zoom in, but that's not what I'm talking about. I'm talking about perception of depth. So when you have the human eyes, they have a very wide field of view, meaning you have this peripheral vision, and then you have the peripheral vision with humans is all kind of blurred out, but you still have it. And that's kind of what they try to do with cameras. It doesn't work that well because it's not wide enough. To get cameras very wide, you either have to have an even bigger lens, which is what they do with video cameras, and that's why they look more natural. Or you have to start curving the lens so that the light from the side starts coming in. So human eyes work differently, very differently to cameras, and you can't, unless you have a huge lens, you can't get that really wide field of view. Field of view means how much stuff you can see around you. They'll also call it framing, whatever fits in the frame, because the frame of the camera is usually a rectangle. It's not like the human eyes. The frame of human eyes is kind of like this, I think, something that's kind of like goggles maybe. So So when you have a lens that's a good lens, they say the more glass there is in a lens, the better. They'll have like different types, different shaped glass in there, and then the quality of the glass will be like some kind of special stuff. And that if it's special stuff, that the quality of the glass is, whatever light comes into it will be filtered through this glass in a way where, this is hard to describe because you don't actually know what these photons are, because they're not actually visible there. Excuse me. You can measure and observe these things, but you can't get a microscope and look at some subatomic particles and stuff. So when they go through glass, you can measure and see what happens to them, but you can't figure out why. And so when some of it goes through a lens, they can see if it's sharper. Sometimes it's sharper, sometimes it's blurrier, sometimes it's bigger or smaller. It seems like it's further away. The only way that I can describe in my own way, so I'm describing this in my own way because this isn't very complicated, and I don't know, so it gives me something to talk about. So when you use your human eyes to see something, and let's say it's a distance of 10 meters, the way that the eye works with the neurons and the shape of it and all that stuff, there's a certain perception that you have where your brain goes, that object is probably at a distance of like 1 meter there. And that 1 meter distance to your brain there's like a feeling to it related to the shape of the object that you're looking at and the light that hits the object, for example, the fan over there. But if you have a lens, it doesn't function like the human eye. That 1 meter distance can seem, because it'll obscure the image slightly to the point where you can't really notice that it's bigger or smaller when you're viewing it on a computer screen, but you can kind of notice there's something a little bit off about it. And what would be off about it is that it's slightly bigger or smaller, or the light is slightly hitting it a different way, and so it doesn't seem quite right, but you can't really tell exactly why. You can say, oh, the light's not quite right, the color's not quite right, the shape of it may be quite kind of wrong, and things like this. So the very expensive lenses, they sit there and they try to make sure that the very expensive lenses produce this image when you stick it on the camera that just looks good. Doesn't have to exactly be like matching the human eyes, but it basically just looks good. And the general rule of thumb is that the more glass and the more high quality glass they put in these lenses, the better the image comes out. So the glass does something to this waveform that will obscure the image. So they use a lot of different words like noise, distortion, and things like this in physics to describe. So every time you put an audio signal through circuits, it'll create this noise. It'll slightly lose some quality. And that's what happens when you push photons, which is like, you think of it as an audio signal, because it's a waveform. That's what happens to photons when you push them through glass. Some kind of distortion happens. And so the color can change. You could say that the obvious things that could change would be the color, kind of the shape, the perceived distance, and things like that. And so what happens with the human brain is that it works in some kind of way where it, all these little differences kind of add up. And so if you look at those, what do they call them? They're like those funny drawings where you can see multiple things in one, or there's a man going down the stairs and then up the stairs and then down the stairs, and it looks like he's going up and down, but he's just going around in circles. So the brain kind of works in some kind of funny way, and then if these things don't really match up in terms of how the glass is manipulating this complex photon waveform, it ends up looking kind of off, and that's what happens in the cheap lenses, is because they don't spend enough time, and because they're cheap, so they're not going to spend too much time creating something that looks good. And so if you use the cheap lenses, you kind of notice that it doesn't look quite right. Like the background doesn't look like quite right to the foreground. There's like, it looks a little bit bent, like the faces look a bit bent or something. So the other thing that the cameras, so that's the thing with the lenses. So the lenses are kind of like half the story with cameras, and then the actual camera, if you want a very good image, they say you have to use a large sensor, but the human eyes don't really work like cameras, and so the human eyes see everything in focus. Everything that's kind of like right in front of you will be in focus, everything else will be blurred out. And so they use this effect with lenses and cameras that is similar but works better with expensive cameras, because with cheaper cameras, if you use this effect where you blurring out the background and keeping the foreground in focus, it kind of looks artificial. It almost looks like the background is very kind of blurry, and there's a man who's kind of like standing there in front of like a green screen or something. Okay, green screen is like one of those video things that you use for movies or advertising, where they put a fake background behind the person. And so what the expensive cameras can do is they can look at different distances in the background and then blur them differently so it looks more natural. So I generally, for my own video stuff, and iPhones don't generally do that, they don't blur the background, and so that's why I don't actually like using it unless that is on a really expensive camera, which I don't really have, and I'll talk about that. So expensive cameras, when you go outside and someone knows there's $4,000 in your hands or something, it's not like a comfortable feeling. Depends on where you are. If there's no one around, it's okay, but usually if you go outside, there's some people around, and so I'm not really concerned about the camera, but they'll they'll take that off you, and they'll ask you for your keys, or they might like intimidate you, or I don't know. They could even get violent. So drawing attention to yourself in a crowd of people by having $5,000 in your hand is kind of like, because the cameras don't, like the iPhones are about 2,000, and they have this iPhone tracking. So that iPhone, I'm drawing stuff for no reason now. That iPhone tracking stops most of the thefts, because you have a map to see where your phone is, but you don't have a map to see where your camera is. And so, and a lot of them have these neck straps, so you put that around your head. And so I never used to actually have that. People have it around the shoulder for that reason. They're quite heavy, so anything like with a big lens and expensive body camera would be like 6,000 maybe, for a better lens and a better, so you have that around the shoulder. And it kind of depends. Most places where I go, I don't think I'd have a problem. Now, figuring out exactly which one you would want to buy at this price range is another problem. So at the moment, I think I just want something that's kind of little, so I don't have to think about this theft stuff at all. It's just something that is better in terms of the image compared to an iPhone. Alright, that video is now long enough, I think. So that's basically it in regards to cameras. When a camera is on manual mode, I adjust a lot of things that you don't adjust on automatic mode, such as, I don't know why I drew a square, it's just something, I guess that's a camera, there we go, camera. So inside of here is something that works a bit like the retina of the human eye, which can contract and retract, I guess. So if it enlarges, it lets more light into the eye, and if it's small, it doesn't let as much light in. So that's the same thing with the camera at the end of it's called a shutter. And then you have, so you can choose how much light you want to come in, but then you can also choose how quickly you take a picture. So the shutter speed can be very long. It can be like, so if you're doing night photography and you're trying to take pictures of galaxies, you could set that to 15 minutes or something and call it a 15-minute exposure, and that's how you do that. So that's the shutter, and then you have something called ISO, which is International Standards Association. It's just a bunch of numbers. It basically just determines how much, what they call exposure, or how much light comes in to the sensor. So if you have way too much light coming into the sensor, everything's white, everything's washed out in white. It's too much light. So there has to be kind of a balance between just enough light and not enough and too much. And then that all has to do with something how the sensor and the processor works in terms of all that stuff. But that's basically it. So branch education, if you watch that, you basically figure out all this stuff, and I don't know, that's basically, it's a bit stupid. Everything's a bit stupid, but I've had a really hard time trying to figure out what the difference between these small cameras is. So this particular one is only like this big. It's extremely light. So it's actually nicer to hold than an iPhone if you go outside. Or inside, or if you're just using it in general. And that's the lesson for today. I might do lessons like this. I was going to do some videos like this on physics, but that's basically, I just said everything there is to say in that, like, I just visualize that pond with a pebble going in, and that's your key to understanding everything we know about the universe, basically.